Hey guys, welcome back to part 2 of the series on this channel on how to build your own blockchain in C. So if you did see the previous video, you will know that we currently have the basic foundation for a very simple blockchain in which we have created two blocks that are linked together using their hashes. So we have the previous hash of the first block, the Genesis block, set to 0, and then the second block is actually linked in the blockchain because it has the previous hash set to the hash of the previous block. So that's what we basically covered in the last video. In this video we're going to work on with what we've already done, but we're also going to add the implementation of the proof of work system, also known as the mining. So this is essentially going to make it more realistic to a real life blockchain in which you would have to have miners to verify each block and take a specific amount of time to do that before they would just be instantly added to the chain. So let's go ahead and get started with that. We're going to go back into the C file here that I've got. And this is just the same code from last video, so we're going to follow on straight away. Now, if you remember last video, we did create this extra integer variable inside the block struct, which was the nonce. Now, we haven't actually used this yet, but that is because this is for specifically related to the mining and the proof of work. So we're going to be using that in this video. Now, we actually need a new function before we get on with anything. We need a function that's actually going to allow us to mine a block or prove or verify a block, essentially. So what this function is basically going to do is it's going to repeatedly call the hash function, which we've already written from last video, and it's going to keep calling it but with a different value for the nonce each time. So it's essentially going to increment this value, and it's going to keep calling the hash function until the hash returns a specific hash that meets some specific criteria, and then when it meets that block will then be verified and we can add it onto the blockchain. So you can actually choose your difficulty you want depending on how long you want it to take for a block to be verified. Now, in the case of Bitcoin, if you go into the blockchain explorer, you can actually look at the blocks. So that this is the latest block. We click on this one here, and you can see the hash of this block. Now, this is actually the hash here, and you can see it starts with a bunch of zeros, and I think it's actually 19 zeros. And that is the current difficulty level set on the blockchain system. So essentially what this means is that miners, or collectively a group of pool mining, will have to repeatedly be guessing a hash for this block until they find a hash that, or until they find a nonce value that produces a hash that starts with 19 zeros. When they have one that starts with 19 zeros, then it's verified onto the blockchain, as you can see here. Now obviously this would actually take an extremely long amount of time, which is why you have pooled mining and why it takes about 10 minutes for a block to be generated, because it does take a very long time to generate a hash that comes out with this. So we're not going to be doing one that's going to take that long. We're not really going to do one that even takes a few seconds. We're going to be doing this, it's still going to be kind of instant in terms of actual time, but the idea is still going to be there, so you can actually improve, or you can actually make this longer if you wanted to use this in a real life situation. So essentially what we need to do is we're going to write our hash function first, and then we'll work with implementing it down in the blocks in a minute. So this function will just be another int return type because we want to return the nonce value that gives the correct hash, and we'll just call this mine block. And this function is also going to take in a similar data array to the previous one. In fact, it will actually be the same data. And then we're going to essentially just be calling repeatedly this hash function with a different nonce each time, placed at the end of the data, until it generates a hash that meets the specific criteria. Now, the hash criteria we're going to go with in this video, just for simplicity, is going to be any hash that ends in a byte of AA, so a hexadecimal byte AA. We're going to look for a hash that ends in that. So it shouldn't really take too long. It will actually be done pretty instantly in terms of what we will see, but it will show you actually as well all the list of hashes that's gone through until it's actually found the correct one. So first of all, inside this function, we're going to have two integer variables, one representing the nonce value, which is going to be starting off at 0. We will then increment that over and over again. And we also need one for the hash that we're going to basically return from the hash function. We're just going to call this hash1. And we're going to just move this hash function above it, just so we have, so we can actually call it without declare it. So what we're basically going to do inside this function is just have a while loop that's going to keep going around, incrementing the nonce value, and then repeatedly calling the hash function until it finds a hash that generates the specific criteria. In our case, we will go with AA, a byte ending in a hash ending in the AA byte, or an FF byte, whatever byte you choose. Just something basic that won't take too long, but will work for this proof of concept basically. So let's just start the while loop. So we want it going on forever. So while 1, and then we're gonna have a char array. And this is going to be data to hash, just like we had with the other function. and then we're gonna, every loop, we're gonna sprintf, we're gonna, inside of data to hash, we're gonna basically put in the data that was passed to this mine block function in the first place. So that'll be data, sorry, let's format this, so percentage %s and then percentage %d. So we want data, and then we want the actual nonce value, which will keep changing. So what we're going to do then is set the hash1 variable equal to the return of the hash function when passed data to hash. And then at the bottom of the while loop, we want to increment the nonce value, so nonce ++. And then we're going to do a quick check to see if the hash that we returned does meet the criteria. So we're going to do an if statement for that, and we'll do if hash1 and ff, which is a bit masking, bitwise operation. So this allows us to basically get the least significant byte of the hash, and we're going to check if that equals, let's just say AA, or you can use any other byte you want. And then if it does, we want to return out of this loop and return out of the function and return the nonce value. Also outside of the while loop, right at the bottom of the function, since it is an int return type, you need to return it anyway. Even though we'll never reach this area, you still need to return it, otherwise your compiler will complain. And we're going to stick in a debug line here, which is going to allow us to basically see the hash that we've attempted on this go, even if it's not the correct hash, just so we can see the program is going through each hash until it finds the correct one. So we'll just do a printf statement here, and we just want to print out the hash in hexadecimal, so hash1. And that will be inside the loop, obviously, so it repeats it every time. So that's essentially all the mine block function is going to do. Pretty simple when you look at it like this. Obviously, we can play around with the difficulty if you wanted some more real-world used blockchain. You wouldn't want it this simple, because this is going to be done in an instant, even though it does still need to look for the correct hash. It's going to be done within probably like 20 to 30 tries, I would assume. So this is probably not the safest. You probably want something more realistic to the actual Bitcoin blockchain, as we already looked at. That uses something like 19 zeros at the start, which does take quite a long time and a lot of computing power. But anyway, this is good enough for this example. So now we can go ahead and implement this down here inside where we've created the blocks already. So we'll start with the Genesis block. Now what we already did is we actually had the hash attribute set directly to the return of the hash function when passed the whole block data. So instead of doing this, we want to first of all set the nonce equal to the genesis.nonce equal to mine block, and we want to pass in data to hash. And that's essentially going to call that function, go through repeatedly until it finds the correct nonce value that gives us the specific hash, and it's going to return it, and return that nonce value into the genesis.nonce attribute. And then we want to set the actual hash to a new set of data that's going to include that specific nonce, and it's going to hash it again. So there's probably a more efficient way to do this, but I'm just going to repeat this code just for the sake of this video. So we'll just call this data to hash n, and inside of here we want the original data to hash, and then we want genesis.nonce. So it's going to basically add the nonce value onto the end of the data, and then it's going to hash that and set that to equal to that. So that's essentially all of that implemented. We'll do it for the other block as well in a minute, but I just want to quickly show you guys that this does work, and we should see these printf statements printing out the hashes that it is trying. So let's go into terminal and we'll just compile this, hopefully no errors. There we go, and we'll just run it, and you can see now it did it pretty instantly. So obviously this is not really a proof of work because it doesn't require much work at all. It's pretty much instant. As you can see though, we do have all these hash values until it finds the correct one. Now there's actually a lot, so yeah, here we go. Right, so we run it here, and you can see it guesses a hash, it keeps going, and there's very different hashes, and then finally we get down to where the hash equals or ends in an AA byte. So you can see that the last 2 bytes of the hash is AA, and yeah, we also want to know the nonce value actually, so we're going to print that out into the little printf thing we have after this. So previous hash, and we want the nonce value. So that will also be represented in hex, and we'll just stick that on the end here. So genesis.nonce, and let's just redo that. Okay, so you can see here the nonce is 232 in hexadecimal. So it went through this amount of tries to get to the hash that's correct, and that's essentially how it's done. So we can also implement that for the block 1 and every block after it. So you do actually have to calculate a hash before you can find the correct one. Now obviously, as I said, if you want to make this more difficult and actually have people work for the block verification, then you want to set it something more difficult. So maybe check for like 2 of these AA bytes or 3 of them, or however advanced you want it. So I've just done the same thing for the second block, and I've also added a couple of colors so you can actually distinguish between the hashes and the block information in the output. And we're going to run it again, and you can see again it does happen in an instant, as I did say. It's very, very easy mining difficulty, but you can see here we have block 1 at the bottom, and then above it is all the hashes attempts it took to get it, and then we have the Genesis block and all the hashes attempts it took to get that. So it goes for all the hashes. We have again the AA byte, which we've already seen, and the nonce value, so the amount of tries it took to get this hash. And then the second hash it goes for again. It has the previous hash set with the one that's got AA as well from the Genesis one, and then this hash also has AA at the end, who actually has 3 A's, but that was just coincidence. So yeah, you can now see hopefully how if you were to change now something in the first block like we did in the first video, so let's put this A back to a T, and assuming this was a real live blockchain network and the difficulty was actually much harder than what we've got here, having someone change it would modify all the hashes, and therefore they would not end in AA, so they'd have to go through again and repeat the entire verification process or the mining process for every block after. So depending on how long, with Bitcoin's example, it takes around roughly 10 minutes per block to be mined. So you can imagine that if someone had to take 10 minutes per block, or the amount of computing power for 10 minutes, which no one person has actually realistically got, it's pretty much impossible for them to actually cheat the blockchain, because you can see we'll run that again. Let's just recompile it. You can see the hashes are all different now. They do obviously still end in AA because it's rerun through the verification process, but in a raw example that would have taken another 10 minutes, 15 minutes, however long, depending on the specific difficulty of the blockchain. So hopefully this is giving you more of an understanding on how the proof of work system and how the mining works in a blockchain if you are new to this idea. And hopefully you learned something from this video. So if there's anything else you want me to implement into this example blockchain program, then leave a comment down below and I'll consider making more videos in this 2-part video series. And but yeah, that's pretty much it. So I hope you guys enjoyed this video. Thanks for watching. Don't forget to subscribe for more, and I will see you next time.